I would like to first thank the organizers for giving me the opportunity to present my research here today. Today, I'll be talking about probing charge dynamics in nanopatterned quantum dot arrays. And this work has been done in collaboration with Professor Munji Bawendi's group in the chemistry department at MIT. Quantum confinement. So I'm going to start first talking about quantum confinement. When you confine a particle to a small region in space, you have to pay an energy cost. And when electrons and holes are confined to potential barriers in regions of dimensions smaller than the de Broglie wavelength, you start seeing quantization effects. So confinement can be in 1, 2, or 3 spatial dimensions. And this is the figure of a 3-dimensional solid. And if you start thinning it down in 1 dimension, you create a quantum well. If you thin it down in another direction, so now you're confined in 2 directions, you create a quantum wire. And if you confine the electron in all 3 dimensions, you create a quantum dot. And if you look at the density of states for this quantum dot, you see that the density of states is discrete, and your energy levels are discrete, and the quantum mechanical analog of this problem is the particle in a box problem. So when you go to fabricate a quantum dot experimentally, you can do it in 3 ways. You can do it epitaxially, as Professor Ray also talked about epitaxial quantum dots. So you start with the substrate, and you deposit another semiconductor on top, and if there's a lattice mismatch, you start to form islands after forming a monolayer, which is the wetting layer, and the dimension of these islands is in the quantum dot size regime. Another way to confine electrons is lithographically. So you can pattern electrodes with electron beam lithography, and so you confine your electrons with an electric field. The third and final way of making quantum dots is colloidal quantum dots, and this is going to be the focus of my talk today. Colloidal quantum dots have a colloidal synthesis, so they're made in solution by controlled nucleation and growth of the particles. So you have a beaker and you add the chemical precursors containing the metal and the anion sources, and the reaction occurs. So the advantage of colloidal quantum dots is that they're very easy to scale up, and they can be produced in bulk, and they can be produced under non-extreme conditions. So looking at just a single colloidal quantum dot. So a single colloidal quantum dot consists of a semiconducting core, and the size of the core ranges from 1 to 20 nanometers, and it's surrounded out to a radius by these black zigzag lines, which are the ligands. Now the ligands act to passivate the surface, and they also act as a tunnel barrier for the electrons, and they insulate the electrons from the surroundings. So now if you look at the energy versus the density of states for a single colloidal quantum dot, because of strong quantum confinement, the continuum of states now gets reduced to a set of discrete energy levels, and these discrete energy levels in the valence and conduction band resemble the atomic sp and d orbitals of an atom, so hence the name artificial atoms. Now we want to build with these artificial atoms. So just like a classical solid is made of atoms, we can imagine making an artificial solid made of these artificial atoms or quantum dots. So the analogy is very helpful, especially when you want to think about the electrical properties. Just like the properties of a classical solid are determined by the energy levels of the atoms that make the solid and how the atoms stack up in the solid, you can imagine the same would hold true for an artificial solid. But the advantage of having an artificial solid made of quantum dots is that the properties are now tunable. So this is a cartoon of the artificial solid that we hope to make with our quantum dots. And by changing the size of the quantum dot, we can tune the on-site electronic energy. And by changing the ligand, we can bring the dots closer together or move them further apart, thereby changing the coupling between the sites. So we now have a tunable solid. I show this figure from Mark Reed's paper, which was published in Scientific American in 1993. So this Mark Reed was also the person who coined the term quantum dot. So this image basically shows particles of cadmium selenide. These are crystallites of cadmium selenide. Cadmium selenide is a wide bandgap semiconductor. And what I'm trying to show in this image is that if you look at the particles on the left side, they're bigger. So the size of the crystallites is larger. And the particles towards the right of the screen, the ones which appear yellow, the crystallites are smaller. So the point here is that the larger crystallites can absorb lower energy photons, and they appear reddish. And the smaller crystallites can only absorb higher energy quanta, and they appear yellow. So you can change the size of you can change the color that the material appears by changing the size of the crystals. So obviously there are going to be a lot of applications for these materials, and the applications would depend on the type of method that you use to manufacture these dots. For quantum computing related applications and logic circuit related applications, epitaxial quantum dots are more useful. Colloidal quantum dots find a lot of application in solar cells, especially because of the tunability of the dots and the tunability of the band gaps. You can imagine making more efficient solar cells, which would allow you to utilize a larger portion of the solar spectrum. Because they emit different colors depending on the size of the quantum dots, you can make LEDs with them. You can also make tunable lasers. Another direction that a lot of chemists have started working towards these days is to use these colloidal quantum dots to make designer solids. And I show this image from Professor Chris Murray's group in University of Pennsylvania, where he's made these beautiful designer solids with these quantum dots. Especially from a physicist's point of view, these designer solids are very interesting to us because you can use these as test beds to study strongly correlated electronic behavior. And there have been predictions of the existence of charge density waves in these materials. So whether you want to make solar cells or you want to use these materials as test beds for studying some strongly correlated electronic behavior, understanding charge transport in these materials is very important. So how do we go about understanding charge transport? This is a cartoon of the quantum dot solid that I showed before. The simplest way to study transport in this material would be you put an electrode on one end, apply a voltage to that side. You add another electrode to the other end, and you just measure the current that flows out through the material. But this conventional measurement of current is limited. And what limits us is basically, first, the contact effects. As the size of the system becomes smaller, contact effects become important, and they can interfere with our measurements. And also when we measure current, what we're measuring is some average hopping rate. And you'll always be dominated by the fastest hopping events. But what will limit any device efficiency would be the slowest hops. And a measurement of current gives us no insight into what's happening with the slower hops. So the experiment that we propose is to actually use a charge sensor to study transport in these materials. And our ultimate aim is to track the motion of a single electron as it moves in this material. So the outline of my talk today is as follows. I will firstly start by describing the sensor that we use. We are using a narrow channel MOSFET as a charge sensor. I will describe our results to study transport in highly resistive materials using these sensors as proof of concept. I will talk about the limitations of having just a single charge sensor. For the second part of my talk, I will talk about a new technique that we have developed to nanopattern these quantum dot arrays, and we hope that the nanopatterning will help us to probe nanoscale charge dynamics in a better way. And finally, I will conclude with an outlook of our research to use these nanoscale sensors to study transport in these colloidal quantum dot arrays. So we're using a narrow channel MOSFET as a charge sensor, and I will slowly start building this MOSFET. We fabricate these MOSFETs from scratch in our lab. So we start with the simple P-type silicon substrate. We send it for ion implantation and get these source and drain ion implanted. We grow an oxide, silicon oxide, as the dielectric layer, and then we add a top gate. And when we apply a voltage to the top gate, you create an inversion region, which is over here, and this inversion region serves as our channel. So you can have a wide gate for the MOSFET, giving you a wide channel MOSFET, and a narrow gate for the MOSFET, which gives you a narrow channel MOSFET. So the MOSFET that we use is 70 nanometers at the narrowest point. The advantage of having a narrow channel MOSFET becomes clear if we look at the conductance and gate voltage characteristics of our device. So for a wide gate MOSFET or a wide channel MOSFET, the conductance, which is shown in dark blue here, as a function of the gate voltage, is completely featureless. But if you look at the same curve for the narrow channel MOSFET, you start seeing these Coulomb oscillations. And what we have done is, by making the gate of the MOSFET narrow, we've increased our sensitivity to the local electrostatic environment. And so you now have a higher sensitivity with the nanoscale gate. So now we want to use this MOSFET to study transport in this resistive material. So we start with amorphous germanium, which is an amorphous semiconductor, and we pattern amorphous germanium in front of this sensor, and here's a scanning electron microscopy image. So this is our MOSFET gate, and it tapers down to a width of 70 nanometers. And here's a strip of amorphous germanium that we've patterned 100 nanometers from this sensor. So if you look at a cross-section along this black dotted line, this is what it looks like. So the gate is capacitively coupled to the inversion region, and so is the amorphous germanium strip. And our measurement relies on this capacitive coupling. So how do we probe transport in this material with the MOSFET? Our experiment consists of applying a voltage pulse to one of these electrodes. So the amorphous germanium strip, shown in green here, is connected to the gold electrode. And we start pulsing the gold electrode, and as we apply a voltage pulse, charge diffuses through the amorphous silicon strip, and we see that motion. And then we monitor the conductance of the MOSFET here as a function of time as the charge diffuses. So what we see is that when we apply a negative voltage pulse, pulsing from 0 to -1 volts, we see first a rapid response, and then a slow decay of the conductance of the MOSFET, which can be fit very well to an exponential. And then when we pulse it back, so we went down from 0 to -1 volts and then back up to 1 volts, we see a response which goes the other way. And we can fit exponentials to both of these and extract the RC charging time constant. So what exactly is going on? To get a quantitative understanding of why we see these transients and how to interpret them, we think about a diffusion model. So we consider the resistive material that we have here, and there is a capacitance to the silicon substrate. So we essentially have a distributed RC network. What happens when you start pulsing is that charge diffuses, and if charge is diffusing exponentially, you see an exponential response in the conductance of the MOSFET. Now, the charge diffusion is directly related to the conductance of the material, and so because our material is very resistive. So if you just put these numbers into the diffusion equation, you can extract the rate of the decay, and the rate of the decay is directly related to the resistance of the resistive material that we are trying to study. So I would now like to show you the results that we have. So going back to the MOSFET gate and the amorphous germanium strip, let's first try to measure the current that comes out of the material. So we measure the current as a function of voltage, and we see that at lower voltages, say below 5 volts, we can hardly measure any current coming out of the material. But as we go to higher voltages, we are no longer dominated by contact effects, and we start to see a current flowing out of the material. But now we want to do our pulsing measurements and see if we can get a resistance for this where the IV characteristic is completely flat. So we've done this as a function of temperature, and we apply our 1 volt pulse. So we're still in this contact limited regime. And when we apply this 1 volt pulse, we see different transient responses at different temperatures. And the reason why the transients are changing, becoming faster or slower with temperature, is because the conductance changes with temperature, and we have extracted that quantity. So from this exponential fit, we can extract an RC time constant, and the R is basically a measure of the resistance of the material. So we now have a new technique to probe the resistance of very highly resistive materials, and I'll show you how high resistances we have measured. So our device enables both the measurement of charge and the measurement of current. At higher temperatures, our transients become too fast, and we can't measure them. At lower temperatures, conventional current measurements become impossible because we just don't measure any current. So if you look at the conductance of the resistive material that we were probing, which is amorphous germanium, as a function of temperature. So the red dots are the points at higher temperatures where we can't measure our transients, but we can measure current, and we extract the conductance from the current measurements. And the blue circles are our conductance values that we have extracted from the charge sensing measurements. As you can see, there is a very small regime where both of these measurements are possible simultaneously, and there is very good agreement between the two. So I've plotted the conductance as a function of T to the 1/4 because the mechanism of transport in amorphous germanium is variable range hopping, and the temperature dependence is T to the 1/4. So what we've seen here is that we were able to measure resistances as high as 10 to the 19 ohms by just applying 1 volts across the material. While there are many advantages of our MOSFET, there are two more that I would like to highlight. So for some of the materials, the resistive materials that we were studying, we saw telegraph noise coming from the material. And our sensor that was patterned next to the material also detected these telegraph noise in the form of these switches. And by doing a correlation analysis, we showed that this switching was perfectly correlated, so our MOSFET can detect switching noise in a nearby material. Our MOSFET also has single electron sensitivity by virtue of having a nanoscale gate. So this is a simple relation where charge over area is capacitance times the gate voltage. And by having an area of just 100 nanometers squared, if we want to see how much the change in voltage would be when one electron passes through the material, we get that the change would be of the order of 50 millivolts, which is a very measurable change when we are talking about measuring voltage differences. So there are obviously some disadvantages to having just one charge sensor, and the most obvious one is that if you just have a MOSFET, the MOSFET has a gate dielectric, which is the silicon oxide, and there are traps in the silicon oxide. So electrons can tunnel into those traps and tunnel out, and that will give you telegraph noise that comes from the MOSFET. So this is switching noise that comes from our MOSFET itself, and we want to get rid of this. So one way to resolve this is to now use two MOSFETs. So now we have these gate 1, and this is the second gate, and say there's a trap underneath this oxide. What we hope to see is that, so this, if we monitor the conductance as a function of time for the first MOSFET, we will see some switching noise in the first MOSFET, and we will also see some switching noise in the second MOSFET. And if we see a switch in both the MOSFETs that happens at exactly the same time, and is of the exact same duration in both of the MOSFETs, we can say that this is coming from something that's not intrinsic to any of the sensors. So by using two sensors, we can eliminate sensor noise. So we ask the following question: is the switching noise in the two MOSFETs correlated? And to answer this question, we fabricated a test structure with just two MOSFETs. We didn't pattern any material in between. And I plot the conductance as a function of the gate voltage, and we see the Coulomb oscillations that we expect to see, indicating that our MOSFETs are sensitive to fluctuations. And now we just monitor the conductance of the MOSFET as a function of time. We've done this for smaller time scales, and we've done this for larger time scales, and here I show you a 25-second snippet. And as you can see that there is telegraph noise in the first MOSFET and in the second one, but the telegraph noise in the two MOSFETs is uncorrelated. So I will now go back and modify our experiment. Instead of having one charge sensor, we now use two charge sensors, and we have a nanoscale material in between, and what we want to do is we hope that we can track the motion of this black electron as it moves from dot to dot in this quantum dot array. And the next challenge which we face with this experiment is that how to integrate a nanoscale pattern into this device structure. So I now go back to the colloidal quantum dots that I described in the beginning. Here I show you cadmium sulfide, zinc sulfide, and lead sulfide quantum dots. They've been fabricated in these vials, and they're different colors because the band gaps are different. And these figures here are the transmission electron microscopy, or TEM, images of these dots, and this is a single monolayer. So when people want to assemble these dots from solution onto a substrate, the common method that is used is called drop casting. In drop casting, you take a needle, you pull out some solution from one of these vials, and you put a drop on the substrate. And as the solvent evaporates, the dots start packing closer and closer together until all the solvent evaporates and you get a continuous film here. The problem with these films is that here I show you a scanning electron microscopy image of a film over a large length scale. So there's cracking that's visible in these films. So if you're studying transport in such a cracked films, obviously you will not know if you're dominated just by the grain boundary scattering or some other thing that is clearly not visible in this figure. So what we really need is we need nanoscale precision in placing our pattern. We need to be able to pattern them so that there are no cracks. We need electrically conducting films. We would like them to be ordered. And we would also like to have flexibility, to choose a substrate on which we can deposit these nanocrystals. To this end, we have developed a novel approach to nanopatterning these quantum dots. I show here a cartoon of how the technique works. So you start with a substrate, say your substrate is silicon oxide, and then you spin an electron beam or a photoresist, say PMMA, on this substrate. And then with electron beam lithography, we create trenches in this resist. After we create trenches in the resist, we drop cast on this surface, and after we've drop casted, the dots fall into the trenches, and we do a standard lift-off procedure, and we are left with just the pattern. So now electron beam lithography gives us nanoscale control over placement. So this is the transistor gate that I have been showing, and this is a patterned strip of lead sulfide quantum dots that we were able to make. Here I show you some of the other patterns that we have tried out. These were made with cadmium selenide quantum dots. As you can see from the SEM image, the length scale is a micron. We have really nice ordered films. There are no visible cracks. And cadmium selenide quantum dots, since their band gap lies in the optical region, they fluoresce, and the fluorescence looks really nice. And these are two different size quantum dots, which shows that we can get different colors. If you look at the atomic force microscopy, which gives you the height profile of the films that we've formed, you see that they're very nicely structured, and there is no measurable surface roughness to the films that we've formed. So now that we have these nice patterned films, we want to see how the electrical properties of these films differ from the cracked films. So I'm going to call these the macroscopic films, and this is an SEM image of the macroscopic films that we were studying. And then we made a triangular pattern with the patterned films, and let's call these the patterned films. And now I look at the conductance scaled by the thickness times width over length. So if you look at the red points that are for the patterned films and the blue points that are for the macroscopic films, you can see that there is a different slope. And the difference in slope is because the conductivity is now different. So we get 0.16 microsiemens per centimeter for the macroscopic films, and we get an improved value of 30 microsiemens per centimeter for the patterned films. So we have an improvement in conductivity by 180. And that's probably because we've eliminated voids, and we also have improved order in our films. So now we go back and we integrate this in between these two sensors. And if you look at a cross-section, this is what it now looks like. So you have these two narrow channel MOSFETs, and you have this quantum dot film, and it's capacitively coupled to both the inversion regions. So the charge sensors now need to be as close as possible to each other, because the method of sensing is electrostatic. So in electrostatic sensing, the potential falls off as 1 over the distance. But it falls off much faster for us because we also have screening from the substrate. So the potential falls off as 1 over r squared. So our sensors really need to be very close to this material. So this adds another limitation, which is that our nano pattern needs to be very narrow. So when we made this nano pattern 80 nanometers wide, we started seeing some novel electrical effects that I would now like to share. So this is the first patterned films, and if you look at the current as a function of the voltage, you see that it's a very nice smooth curve. Now for the nano pattern that we made, which was 50 nanometers, just 50 nanometers wide, when we measure the current as a function of voltage, we start seeing additional noise in the current. So when we see this additional noise in the current, we want to analyze this additional noise. And what we do first is that, so this is the current as a function of voltage. As a first step, what we did was that we went and sat at each one of these voltages and just measured the current as a function of time. And then we histogrammed the result. So the histogram shows the intensity as a function of the average current. So the average current is higher, and the average current is higher at higher fields. So at lower fields, say between 0 and a bias of 0 and 10 volts, we see that our histograms fit to nice Gaussians, and the width of the Gaussians is very narrow. As you go to higher fields, the width of the Gaussians increases, and it increases very dramatically, and it's a non-monotonic increase. We also analyze this noise as a function of temperature, from room temperature all the way down to 4 Kelvin. So we see that at room temperature, we still see this additional noise, and as we go down to lower temperatures, the noise freezes out. So there's a very strong temperature dependence of the noise, but there's a weak temperature dependence of the average current. If you look at the frequency dependence of this excess noise that we see, it fits a 1 over f to the alpha power spectrum with alpha approximately of the order of 1.3. And we're still working to understand this noise more. So possible explanations are as follows. In a solid, in a classical solid, your electrons are delocalized. But in a quantum dot solid, your electrons, because of quantum confinement, are really localized to each of these dots being shown in the light green. So what you have when you make the pattern more and more narrow is an effectively one-dimensional channel of these quantum dots, and you can have hopping in this effectively one-dimensional array of dots. As you increase the field, as you go to higher and higher fields, certain paths become forbidden because any motion perpendicular to the direction of a strong electric field will be forbidden. The temperature dependence also suggests that some electron-phonon interaction might also be relevant. So with that, I would like to conclude my talk. So we've used nanoscale charge sensors to measure electrical conductance or a regime of high resistance. Our technique is independent of contact effects, and it's sensitive to single electron hopping. We have used two sensors and used that to eliminate the sensor noise. We have introduced a new technique to pattern these quantum dots, and that has led to improved conductivity and improved order in these dots. We start seeing novel electrical effects in these nanoscopic or nanopatterned films, including an increase in the conductivity and the current noise in the IV characteristics. So with that, I would like to thank my advisor, Professor Mark Kastner, for his unending support and encouragement. I would like to thank my group members, Tamar and Kenny, who were co-workers in this project. From the Munji Bawendi group in the chemistry department, I would like to thank Darcy, who fabricated all of the colloidal quantum dots for us. I would like to thank people from the scanning electron beam lithography and the microtechnology laboratory at MIT for help with device fabrication. Our funding was by US Army Research Office and the Department of Energy. I would like to thank the Fulbright and Institute of International Education and the US Department of State for an International Fulbright Science and Technology Award. I would also like to thank the Schlumberger Foundation for a Faculty for Future Fellowship in 2012. I offer my obeisance to the Supreme Father for his continued grace and guidance, and I would like to thank you all for your attention.